Hello again. In this lecture we are going to have a comparison between the shortest path algorithm that we discussed, that is the Dijkstra's algorithm, and the Bellman-Ford algorithm. So starting with computational cost, as we found out earlier, the Dijkstra's algorithm has a computational cost of n plus v into log of n, where n is the total number of nodes and v is the total number of edges. Whereas in case of Bellman-Ford's algorithm, it's n cube, considering n square edges and n is the number of nodes. So it has more computational cost, and that is because graphs with negative weights takes longer to settle down. So that is the computational cost. Secondly, in terms of assumptions, it assumes the graph to have non-negative weights, while Bellman's-Ford algorithm assumes the graph to have non-negative cycles. That is, it may have negative weights, but completing a cycle, that is starting from a node with traversing other nodes and getting back to the same node, should not result in a negative weight. The third is how the updation of cost works. So the updation mechanism for the Dijkstra's algorithm is to update the cost of the nodes that are adjacent to the node in observation, whereas in case of Bellman-Ford's algorithm, all nodes are checked for a possible update of their cost using all possible edges. From that perspective, we can think of it as a kind of breadth first search algorithm, where we start from the source is the root and we keep on exploring the breadth first and then the depth, whereas we do not have any particular order in case of Bellman-Ford's algorithm. So no order observed, and we rather check for all the edges in any order. So that is with respect to the order of checking. And finally, the Dijkstra's algorithm can be applied to both directed and undirected graphs, whereas Bellman-Ford algorithm can only be applied to directed graphs. So before we see how Bellman-Ford's algorithm cannot be applied to undirected graphs, let's observe the problem of Bellman-Ford's algorithm with graphs having negative cycles. When there is a negative cycle in a graph, that means that we can go from A to B, B to C, and then back from C to A, where the net cost is negative. For example, this is -5, this is 2, and this is 1. So as we keep on taking this route, the cost of all these three nodes is going to continue to reduce. So there is no solution to this problem, and therefore even if we apply Bellman-Ford's algorithm, still it's not going to help because there is no solution to it. It may go for any number of iterations and the cost will continue to reduce. So since there is no solution to such problem, the next question is, how can we find if a graph has negative cycles? Either we may use some separate algorithm in order to see if a graph has negative cycles, then applying any of the shortest path algorithm is not going to help because that problem does not have any solution. Luckily, Bellman-Ford's algorithm also helps us to find if a graph has negative cycles. If you remember from the Bellman-Ford's algorithm, we said that the outer loop runs for n-1 times. So if we run an algorithm for n-1 times, we are going to have some cost associated to all these nodes. So let's just try this algorithm again for the nth time. And if the weights continue to reduce, it means that this graph has a negative cycle, because if it wasn't the case, it would have settled up till this point. So this is a very good condition for checking if a graph has negative cycles. Just use the algorithm for one extra iteration, and if the cost further reduce, it's a clear indication that it has negative cycles. So now that we have a clear understanding of the negative cycles and how we can find them and why they do not have a definite solution, so we may come back to this and see why Bellman-Ford's algorithm cannot be applied to undirected graphs. And by undirected graphs, we particularly mean the undirected graphs with negative weights. Because if there are no negative weights, then the Dijkstra algorithm could have been used with lesser computational cost. So now if we take an example of this graph that is undirected and has negative weights, let's say 2. So this undirected graph can also be seen as a directed graph. In fact, we can represent it as we can go from A to B and from B to A, both with cost of -2. So we may look at it as a negative cycle where if we keep on moving from A to B and back to A, the weight of A is going to continue to reduce, and the same is the case for B. So an important point over here is that a graph with undirected edge having negative weight is the same as having a negative cycle. So therefore, any graph with undirected negative edge is the same as having negative cycle, and there is no possible solution for it, and therefore Bellman-Ford or any shortest path algorithm cannot be applied for such a problem. Thank you.